Okay, so let's come back and continue with the class. We're at page 35. So up to this point, then we can move on to the general CRLB for signals in wide Gaussian noise. General means we are deriving a more generic version for this kind of model. But the signal can be general, but the noise is not general. Noise is still wide Gaussian. Okay, we are deriving a generic description for the CILB. Okay, so here it is. Uh, since it's common to assume wide Gaussian noise, it is worthwhile to derive the CILB for this case. Later, we will extend this to non-Gaussian noise. So we assume that a deterministic signal with an unknown parameter theta is observed in wide Gaussian noise as this form. So you have x observation that is equal to s of n theta. And n is what? N is the time index, the index for measurement. So it's not a big deal for n. But for theta, there is something here. S of n theta means signal is a generic signal as a function of theta. So we are not setting a very tiny category for this S. We are setting a more general framework for this, which means if S is a generic or whatever, or a lot of different types of signals, as long as it's dependent on theta, then it fits into this category. All right, so S is a function of theta, then plus noise. Then the dependence of the signal on theta is explicitly noted. The likelihood function is like this: P of x theta equal to this aspect of this, and then uh, this this whole description. This is what review a little bit. This is multivariate Gaussian, right? Multivariate Gaussian exponent and sigma square and summation. Summation means what? Summation means it's independent. If it's not independent, we cannot write it into summation. Okay, so it's independent samples, and then summation x n minus s. How come we have to minus s here? Think about this. If you take the expectation for this, this is going to be sigma square but zero mean, right? Sigma square zero mean. Then what you have is your mean for the sample to be s. That's why s is this position. Then you take the first order derivative, differentiating once. Then you produce a partial ln p of x theta over partial theta equal to 1 over sigma squared summation of this. This is what? If we just take log for this, take log, you see there, this term has nothing to do with theta. Therefore, when it's taken derivative by theta, it disappears. So you don't see this here. You do not, sorry. If we look at this term, it disappears because it has nothing to do with theta. You take log, it becomes, you know, one single term without theta. And then you take the derivative, it disappears. And this term, you take the log, you have this thing coming out. And it comes out, and you take the derivative, you use chain rule. Recall the chain rule in calculus. And then you get the first thing, the second derivative with this, and then the second term is partial this thing, partial theta. Partial this whole thing, partial theta. Then you get first order derivative. Then the second differentiation results in here. You take the partial square, meaning that you are actually taking this equation, put it here, and then take the differentiation one more time, and you get 1 over sigma square summation of this uh, summation of this this summation this summation of this term parenthesis x minus s partial square s minus partial s square. This is again the chain using the chain rule. Then you get this, and you take the expected value for this, right? Take expected value, then we are going to take a negative, and then we are going to put it at where? At the denominator, right? Recall the beginning of this chapter if you don't remember details. We will take the expectation, take a negative sign, and put it in the denominator. All right, that's the CRB. Okay, so second order derivative is obtained. Then we will take the expected value. If you take expected value, this thing expect with this is going to be what? 0, because expect of x is equal to s minus s, which is 0. So this term is 0. And this term is 0, then this is gone. And what remains is the summation with this. So it becomes a summation with this, which is this term. So you take the expectation, this term is gone, this term stays, and it has a minus sign here. So finally, we put this at the denominator and then take the negative sign. And negative, negative meaning positive. So you have a positive here. So you have sigma square. Sigma square is because you have a 1 over sigma square. When you put it at the denominator, the sigma square comes up at the numerator. Okay. So this will be the CRB. The form of the bound demonstrates the importance of the signal dependence on theta. Yeah. How come? What's the importance? See this? Partial S partial theta. The signal dependence. The signal dependence is reflected in this partial S partial theta. Let's say if you have a signal that's highly dependent on theta, then your estimator will have better performance. How come? Because it depends a lot on theta. Then when you take the derivative, it will be larger, and it's square. Larger square is larger. So you have larger value here, then you have smaller CRB. In the other direction, if you have S that is the less dependent on theta, so that value will be small. And when it's in the denominator, the whole thing will be large. Then you have poor performance, right? So it really reflects the signal dependence on theta. Signals that change rapidly as the unknown parameter changes result in accurate estimators. Then we have some examples in the previous chapter. Okay, so we have sinusoidal frequency estimation, and I'm going to just skip this and leave it for your reading. You can see here you have S as a function of F0, but F0 is in fact the frequency component. So you plug it into this equation, you get something like that. Okay, so but if you plot it all with respect to frequency, you see different frequencies, different accuracies. Then the transformation of parameters. Oftentimes Fourier transformation. A frequency occurs in practice that the parameter we wish to estimate is a function of some more fundamental parameter. For instance, example 3.3, we may not be interested in A, but instead we wish to estimate A squared, or the power of the signal. Recall that when we talk about signal, we take the square, we will think of it as the power, the signal power or signal energy. And then knowing the CRB for A, we can easily obtain for A squared or in general for any function of A. So it can be proved, but we are not prove it here. We don't prove it here. We just show you the outcome. If we are estimating a parameter, that parameter alpha is a function of the sort of the ordinary, more ordinary parameter theta. So we call it alpha as a function of g function of theta. And that g can be generic, okay? G is not confined to any specific format. It can be generic. So alpha will be g theta. Then the CRB will be larger than this. You see the denominator doesn't change. The numerator becomes what? Becomes a partial g over partial theta squared. If we go back to the ordinary CRB, let's take a look at what happens. The ordinary CRB, we'll review one more time. The ordinary CRB is 1 over here, 1 at the numerator. And now we have a new version of the CRB, which is a transformation of parameter. Instead of 1, we put in partial g, partial theta here. So for the present example, this becomes alpha equal to g of A equal to A squared. And then if we apply this rule, variance of A squared hat will be larger than n over sigma squared. This has been done before, this part. It's n over sigma squared. And then partial g is partial A squared partial A, right? Which is 2A. So 2A squared. Then you do some simplification, you get something like that. So notice that in using this equation, the CRB is still expressed in terms of theta rather than the alpha. In this case, we are interested in A squared hat, but remains it's expressed in the as a function of A. Okay. So the other things is we saw in example 3.3 that the sample mean estimator was efficient for A. We have done that many times. It might be supposed that x bar squared is efficient for A squared. I mean, trivially, conceptually, intuitively, you would think that way, right? People would just think if x bar is good, then x bar is supposed to be good. S bar squared is supposed to be good for A squared. But let's see what happens. Let's see what happens. To quickly dispel this notion, we first show that x bar squared is not even an unbiased. Since x bar is distributed this way, let's take the expectation for x bar squared, which is equal to E expect of x squared plus variance. This can be done by doing statistical derivation, variance of x bar. Then expect of x bar is A, so expect x bar squared is A squared plus sigma squared over n, sigma squared over n. So immediately conclude that efficiency of an estimator is destroyed by a nonlinear transformation. Because you take the square, then it's not even unbiased. It becomes biased, not to mention other properties. It's all destroyed. So it will be maintained for linear transformation, but not nonlinear. For example, take the square, those things, it will be destroyed. The property will be destroyed. So let's see another example. if we are interested in g function which is equal to a theta plus b, then what's going to happen? Our estimate of g theta, we will choose g theta to be equal to g of theta hat equal to g a theta hat plus b. Okay, I mean this is a choice. As we said, there are many options, possibilities, different kinds of ways to design the estimator, but this is an option and we choose. This is not to say that we would just say this is the best. No, we cannot say it that way. Okay, we have to do it this way and then verify it later. Then we will say it has some nice properties. But before we do that, this is only an option. This is not a solution yet. Okay, so we have A theta hat plus B. Then you take the expectation and see what happens, which is equal to alpha E. A expect of theta hat plus B, but theta hat is supposed to be assuming unbiased, right? The original estimated theta hat is assumed to be unbiased. As a result, its expectation is theta. So we have A theta plus B, which is G theta. So if you take the expectation for the estimator, which is equal to true value, then G is unbiased. The CRB for G, then of course we are taking that transformation equation here, transformation equation. Then what happens? We are having this partial G partial I at here, and again visual information at the numerator, and then of course you go through some derivation, you get a squared variance of theta hat, but variance of G theta is equal to variance of a theta hat plus b, which is equal to a squared variance of theta hat. How come? Because when a is invariance, you take it out, it becomes square. That's in our fundamental statistics theory. So you take it out, you get a squared, and then variance of a constant is nothing, it's zero. So you get variance of theta hat. So you see, we go through derivation, we get a squared variance theta hat. But if we take the variance of the estimator, we still get a squared variance theta hat. It's the same thing. As a result, we say CRB can be achieved. And we are not saying this for a specific A or B. No, A or B can be general. As a result, we will say as long as it's a linear transformation, this thing is linear transformation, then we will say CRB is maintained. Is maintained. Although efficiency is preserved only over linear transformation, it is approximately maintained over nonlinear if the data record is large enough, conceptually. Conceptually. Okay. So I think it's important to recognize if you have a transformation for the parameter, then this is what you do. And there are some property, for example, nonlinear transformation, then it's not even efficient. And linear transformation, here, we prove it's efficient and it attains the CRB. But for nonlinear, then what happens? We cannot say anything about it. But if the record is large enough, then it's approximately maintained. That's all we say here. Okay, so let's take a break for a couple minutes, then come back.